So this lecture, we're going to switch topic, talk about PCF, which is a language for partial functionals rather than total ones. And of course, it's the little toy prototypical language that really, like, in some sense, lies at the heart of functional languages like Haskell and ML. So quick recap of what PCF is. And then we're going to look at a certain model for PCF, which I call the Nested Sequential Procedure model. And the way to get an intuition for this model is to look at lots of examples. So we're going to look at lots of examples. And then we're going to explore some of what you can prove using this model. We can show that this model has lots of interesting submodels. They correspond to various sublanguages of PCF that may be interesting. And so one can prove certain things about the expressivity distinctions between those sublanguages. And then probably in extra time, there's a bit of bonus material about how all this is related to game semantics. So the ideas here have a long and complicated history, as you can see by all these different names there are of people sort of trying to get at roughly the same essential concepts from slightly different perspectives. I've said in my abstracts that in these talks about classic material, but I feel like we're perhaps a bit more nuanced here. So certainly these ideas do have deep roots and a long pedigree, so classic ideas in that sense. But the particular embodiment of these ideas that I'm going to talk about, the nested sequential procedure model, is just the version of these ideas that's preferred by Dag and myself from today's perspective. But it can't really claim any definitive status, and there may be colleagues, for instance, there may be colleagues in game semantics who think this would all be much clearer if you presented it using in terms of games. For me personally, it isn't, but that's just personal. And then some of the applications of this model, the sublanguages and substructures, these were new in the first edition of the book, so I certainly can't claim classic status for those. Although they do perhaps contribute to the evidence that these ideas do have some genuine mileage in them. Okay. As you all know, I have kind of too much to say, too much to get through. So perhaps what I suggest is if people are willing to confine their questions just during the talk to clarifications of things I say or on the slide, and save interesting follow-up questions, side questions for the time afterwards, that will be great. So probably most of you have seen something like this. Plotkin's PCF is a simply typed lambda calculus over n with some simple constants. So we've got all the numerals. We've got successor, predecessor. We've got if zero, which lets us write expressions conditional on whether first argument is 0 or not. And most interestingly, we have this fixed point or recursion combinator. So given any operator from sigma to itself, this gives you something that is a fixed point of that operator. And as is pretty well known, we can use this as a way of writing down recursive definitions of functions. So here's the reduction semantics I'm going to use today. So call by name semantics following the original version of Plotkin. We've got the beta rule, some obvious rules for successor, predecessor, if zero, and then this killer rule for the Y combinator. So if we say y of m, so m is a thing of this type, sigma O sigma. So if we're claiming that that computes something that's a fixed point of m, it ought to be possible to replace ym by m of ym. And indeed, that's a useful thing to do and lets us do computations by recursion. I have a little example in just a second if you're a bit rusty on this stuff. And then we can apply these rules in certain positions. So we generate our evaluation contexts like this. These are the places where you can apply these rules. And here's a little example, just in case you're refreshing on this stuff. So double, that's a function that takes x to 2x. We read that as this is the fixed point of, okay, so as it were, it computes a solution to the equation f equals this thing, which is itself defined in terms of x. So f equals the function which returns 0 on 0, and otherwise looks at the value on the predecessor as a double successor on it. So if you can make sense of that, it's good. What do you think? Thank God for modern high-level programming languages, kind of, which write this stuff much more readably as a recursive definition. So hopefully that's kind of familiar. This is the original PCF, or a small variation on. It's, as I say, it's a call by name language, but we're also going to be interested in a little bit of call by values. So we're going to add this operator, which, for those of you who know, this corresponds to the strict application operator in Haskell. So this operator, it takes a function n to n and a thing of type n. So here, rather than being allowed to just pass the argument in the argument in unevaluated, this forces us to evaluate the second argument to a numeral, and then we just call n on that numeral. So by making this an evaluation context, that means that if we have a term like this, we reduce this second argument for as long as we can. And if we get a numeral, then we can switch to this rule. So yeah, we have this just at ground type, because in this version of PCF, we're not making any kind of value versus non-value distinction at higher types. Phil?
Right, thanks for that, John. So one thing you don't draw attention to is, if I'm remembering right, in Plotkin's original paper, if zero, the second and third argument and the result are all arbitrary sigma rather than n. But that in fact doesn't change the power, because you could just use the expansion.
So once you're quite right. Once you've got this conditional at ground type, you can define the conditional at high type from it. So it doesn't change the power. Yes. Thanks.
And is there some reason that you changed it from what Plotkin did? And am I remembering correctly?
I think just to minimize, I'm interested in having a small number of primitives of low types as the sort of core of it, and then looking at things like y sigma that you can add. I'm interested in sort of minimizing the basis in some sense, if that makes sense. But there's no variation.
Okay, and then by val, you could just define by val in terms of the other stuff that's there by just recursing on the second argument, the one that's of type n, and just
you can define something. Yes, that's I did mean to say that. So so you can define something observation equivalent to this in plain PCF, but it won't have the same evaluation behavior. So we're going to be interested in something more fine-grained than observational equivalence in PCF. What functions that you can compute. What functions you can compute. So we'll see that when we look, we'll see very soon that actually our model is crying out to have this by val added, and the language is in a certain sense incomplete without it.
Okay, I guess you'll clarify why defining it doesn't work when we get to that point. That's great. Thank you.
Okay, cheers. Right. So maybe before I introduce this model, I just want to say a bit about the kind of thing it is and where it sits among other things. So in the classic work, we had PCF, which is a world of concrete programs, and Scott and Plotkin gave the denotational semantics of that in the abstract mathematical world of Scott domains and pure mathematical functions. So we go from something very concrete to something really pretty abstract. So this model I'm going to talk about kind of sits in between those in terms of its level of abstraction. So NSPs are, I'd say, much more abstract than actual programs, but quite a bit more concrete than pure mathematical functions, because they have information in them about order of evaluation. And that's why, in response to Phil's point, so at this level, you can distinguish, by val looks different from, a sort of imitation by val that you could write. So we see distinctions here in NSPs that we don't see at the level of Scott domains. I think PCF Bohm trees is a good name for these gadgets. Anyone who knows about Bohm trees for untyped lambda calculus. The reason we don't go with that name is we want a name as it's part of the what we show in the book, that this world of nested sequential procedures serves equally well as an interpretation of an old thing called cleanly computability, which has an interpretation in the world of sets, which, as we showed, factors through NSPs in the same way that the Scott domain interpretation of PCF factors through NSPs. So there's this common world of processes or algorithms that arises in both contexts. Perhaps I can say, yes, at this point, why we really want bival. So when we add bival to the language, it becomes true that every computable element in this NSP model is actually the denotation of some term in PCF plus bival. That's not true without bival. So this is sort of, bival is what you need to add to get this completeness result there. Okay, so that's orientation. Now, this is the main definition of the main concept of the talk. So this is what nested sequential procedures are. They're kind of terms in an infinitary language. So they're terms with an infinite syntax. So we mutually recursively define a class of procedures, which we can think of as modeling programs of any type, sigma, and a world of expressions, which we think of as modeling expressions of type n that we're at in the process of trying to evaluate. So procedures are all lambdas, and yeah, so let's just see what they are. So a procedure, which will have a certain type, will have the form of a lambda binding of a number of variables, which are as many variables as you need to get down to something so that what remains is just something of type n, ground type. So we can think of these procedures as in some sense fully eta expanded.
Can n be 0?
Yes, I'll come to that. Yes, that's a good point. N can be 0 here. Yeah, and so there's a distinction between, yeah. I may as well say it now. The procedure lambda dot e is like a thunk, which you can pass around without evaluating. But an expression is a thing you're actually currently trying to evaluate. If that makes sense. Okay. So to give a procedure, yeah. So this is what procedure is. And now, how can an expression behave? So an expression. Think about what happens with a ground type expression in PCF. You can try to evaluate it. Either the evaluation will just run forever, it'll diverge, in which case you can we'll just write bottom. It'll diverge, as it were, without consulting or looking at any of its arguments. Okay, or it might return a numeral, again without looking at any of its arguments. Or at some point, it will need to actually consult one of its arguments, one of these variables that are around one of these x variables, to get some further information on it. So typically, these variables themselves, they could be of ground type, they could be functions, but in general, we pass, if we want to get some information about from x, we pass x some arguments, and again, we have enough arguments here to get something. To make something of ground type, and then we branch according to the result of that. If this gives us a numerical result, we've learned some genuine information. So this is where the syntax is infinitary. We have an infinite branching here with a branch, a new expression ei for each I. Okay, so trees can be infinitely broad, as it were. And just to, just to finish this off. So all of this is typed. I won't go into details, but variables are typed. So there's an obvious notion. So if we've got this of what it means to be well typed. So when we've got an application of here, the number and type of these QRs had better fit with the type of X. What does it mean for the type of QR to fix? Well, these Qs will have this form. So these variables X, I here, and better all tie up. Okay. We allow n equals 0, so we write lambda dot e, and that's a kind of func for a ground type. You can think of that as a func for a kind of ground type expression. We also allow r to be 0, so we sort of have to bear in mind that when we can write case x of something. We have to bear in mind that there's a sort of secret application here to 0 arguments. It's like this func is being forced there. I've chosen not to include that in the notation today, but that's how it is. So, as it were, these we make a clear distinction here between getting information from the arguments and returning information based on what we know. So we would not notice that we're not allowed to write just x as an expression. If you want to get the value of x, you have to write case x of, if it's I, then we return I. So we're separating out the step of extracting information from the argument we're given and the step of returning something. Yeah.
I feel like you've explained it, but I can't quite grasp it. So the QR, the Q1 to QRs are arguments that you're passing to X, right?
Mm-hmm.
But it's an expression, so computationally, what does that mean? Like, at which point are you evaluating those procedures?
So we suppose X is an argument we've been given,
Right.
and we feed that argument with these procedures which we construct.
Right.
And then it's over to the argument we've been given.
Procedures aren't evaluated, right?
Sorry?
The procedures aren't evaluated at that point, right?
It doesn't mean anything to evaluate a procedure.
Okay.
It only really means some.
They're lambdas, they're stuck.
Yeah, they're stuck. We'll see lots of examples. Really will help with the intuition. Okay. And the other thing to say is, as well as being infinitely broad, these trees can be infinitely deep. So if you understand this definition co-inductively, as if it was like a data type of lazy trees or something like that, this will have the sub expressions, the Q's and the E's here, and these themselves can be expanded and go on forever. So we'll see examples that show how trees can be infinitely broad or infinitely deep.
So wait, this is different from Berm trees, right? Because usually when the Bermification of a
Can I treat that as a side? Sorry, can I treat that as a side question? Because I'm very happy to. So here's a first example. Here's what the tree would be for lambda x y. If x equals y, then 3, else 5. Well, what happens when, so given an x and a y, what happens when you want to try and evaluate this? Well, you'll first evaluate x, and then you'll get some information from that. You'll know what x is, and then in this tree we branch according to the information we've got. So if x is 0, we do this. In that case, well, then next we evaluate y. At again the empty list of arguments, and again we branch on the result. And in this case, we see that if x and y are both 0, we return 3. Otherwise, we return 5. If x is 1, y is 0, we return 5. Y is 1, we return 3, and so on. So this is just a sort of simple doubly infinite tree. Hopefully that agrees with your intuition of how this program works. Okay. Right. How about the if 0 conditional? So we're going to sort of if 0, the x, then if x is 0, then y, else z. So but we evaluate x. If x is 0, then we evaluate y, and we return whatever y gives us. If x evaluates to anything else, then we evaluate z and return whatever z gives us. So hopefully that's okay. Now, so I'm going to go working out something slightly more advanced. We've got two kinds of application here. These are both applications of an NRON thing to an N thing. So the ordinary application, which you could write like this, or you could just write it as the identity, because the eta rule is valid in everything's eta expanded, so the eta rules are valid in this. We don't see distinctions between those. So here, so we're given an f and an x. What do we pass to f? What we pass to f is something which itself is a procedure, and this is like a thunk for X. So this is a thunk which, should we choose to evaluate it, will evaluate X and then return whatever that value of X was. Okay, and then whatever that evaluation of f of this thing gives you, we return that. So we should get pretty tired of seeing all this 0 goes to 0, 1 goes to 1. I'll include those for the first few, so that you get the idea that they're really there. Okay, so this is the sort of ordinary application, the ordinary application, or if you like, it's the eta expansion of the identity. What about the strict application, called by value 1? Here we start by evaluating X. Okay, so we evaluate X, we get a number, and then wherever that number is, we can feed the thunk for that number to F. Okay, so that thereafter there's no need, there'll never be any need to reevaluate X. We've already got the information we need, so we're just passing that to F, and we get yeah, whatever that returns, we return. So is this sort of making sense? Yeah, great, thanks. So we can see these distinctions. Yeah.
Question, Phil?
Just to try to understand, I was a bit confused that you didn't just write case f of x, and the reason you didn't write that is it's not permitted by the grammar you've given.
That's right. The arguments we're kind of the grammar have given sort of f has to, the things you apply f to have to be themselves procedures, and this procedure here is the procedure that plays the role of just x. But so there's a lot of eta expansion going on here to make things in this kind of normal form.
Right. And one thing that you might do is do a case on x, and then later on in one of the branches again do a case on x, but that second one is redundant.
Yeah.
Is that allowed, or the redundant one's not allowed?
Good question. That's allowed. And what that will mean is that as long as we're within the world of PCF, there will be then unreachable parts of the tree, because if you the branches where you have two different values for the two evaluations of x will then be not reachable if you're in a purely functional setting, which we are at the moment, but it is permitted. Yes.
Okay, so we can have things that have the exact same semantics, but will still have different nested trees.
Yeah.
Right. Okay.
Yeah.
Just to make sure I understand that, the first case, you first evaluate the f on the procedure, and then take the result of that and return it. Is that correct?
Yeah. So we pass F this thunk, and then it's up to F whether it ever evaluates.
Right. So you evaluate that first, and then you look at the result and look at the right hand side. That's what that means.
Well, you evaluate F of this.
Yeah.
Yeah. And then whatever you get from that, that's your answer.
And that would maybe not evaluate that.
You might, yeah. At any point, there's the risk of things not about. If either participant just goes undefined, then the thing will. Okay. So this is a slightly more technical slide, not so important, but just to show that I'm not completely making these trees up. So there is a system, even without making these NSPs into a proper model, there is a systematic way we can compute the NSP for a PCF term just by successive head reductions to head normal form. So, for example, if we want to know, we've got an M of this type, we want to know what its tree is. Well, let's try feeding M with some fresh free variables X and see what happens. Okay, so we try and reduce this using the normal rules of PCF, carrying these free variables around. If that goes on forever, then
That's how do you compute that?
oh yeah. There's something. Yeah. It's a concession to a classical way of thinking that I've written this actual bottom symbol here. Really, bottom. A more computable way of doing it would be to write nothing at all. You don't know that there's a label there, but from a sort of infinite perspective of sort of we allow ourselves to see from time omega, as it were. whether we've ever got to. But thank you for that. That's a good point. Okay. The tree will be yeah, if it computes forever, we've got a bottom on our hands. If it evaluates to a numeral, then we've got a numeral. Otherwise, we might get stuck because we get to a point where we need to know what one of these x's are. So we've got this application of some x appearing in an evaluation position like this. And if we come in that, then we can see what the NSP has to be, because what we're saying is this is the kind of first thing we need to know to make further progress. So the NSP will have a case expression at this point. And what we pass to the x will be the NSP is derived from these arguments p. So we recursively do the same to compute these. And then what should go here? Then we say, well, supposing this call were to return I, okay, how would the program proceed from then on? So we can do that just by plugging I. So that should be a curly e there, curly e of I. Plugging I into this evaluation context, see how the computation would continue if this call were to return I. And we do that for each I. So you can grow a tree from in a top-down way from a PCF program like this. So that gives you enough to sort of know in principle, you can verify what I'm saying about the trees of various kinds of programs. Now let's look at some bigger examples. So now we're going to look at, right, yes, we do indeed. Now we're going to look at various kinds of recursion and iteration constructs, and we're going to compare them. So these trees, they're not just examples, they're kind of all material for the talk. So yeah, let's look at a simple example of a fixed point operator. So the simplest interesting one, this type here. So recall that y of f expands to f of y of f. So it would also be true that y of f applied to an x will expand to f of y of x applied to an x. So the idea is for this y, we get given an f, which will be a type 2 thing, and an x. As it were, we unroll the recursion like this. So we start by applying f to something and see what the result is. We apply f to something and we apply that to x, or rather the thing that does duty for x within our grammar. So this, I write x eta for this expansion, which I think of as a kind of eta expansion here. Whatever we get, that we return. Now, what is this thing we apply f to? Well, that itself is y of f. So we've got the same thing down here. I've just used a different variable name for the x. So we've got, so you can see that this, yeah, if you work out, this recursion generates this sort of infinite path of nested calls to f through the tree. Of course, any given terminating computation will only explore that to a finite depth. But this is saying that our Y Combinator in principle has the potential to go as deep as you ever want it to. So this is an example where we have an infinitely deep tree, and indeed infinite nesting. That's going to be an important theme, the idea of infinite nesting. Okay, so that's for this simple type n arrow n. For a general type sigma, basically a tree has the same shape. We replace our single variable x here by this list of variables, and we do this eta expansion thing to turn them into procedures. And as the types go up, the way that you have to do that gets a bit more complicated. So we, in general, we expand a variable to a procedure in this hereditary way. We write this, and then we, in terms of the expansions of these variables z, which have lower type than 1. So we've got a kind of inductive definition of this eta expansion, which is just the way to turn a variable into a grammatically correct procedure. But modulo that, the tree for y at any type sigma is the same has the same form as above. Okay. Important 3. So bear that in mind. Let's okay. Let's now look at some of the system T style primitive recursors that we saw in lecture 1. And today I'm going to write the types of them like this. Slightly convenient to swap the order of these 2 arguments there. I hope this won't trouble you too much. So at ground type, the ordinary primitive recursor at ground type, if you want, you can write it. You can write it as a recursive using the Y combinator. You can write it as a recursive program like this of dubious readability. So the point is to evaluate rec A F n. We evaluate the n first, and then do various things. So here's what the tree for it looks like. We evaluate the n first, and then we branch on what it is. If n is 0, that means we just want to return the starting value A. And here, this A is officially case A of I arrow I, but I've just, at this point, deciding to suppress some of these things just to reduce clutter. If A is 1, then what do we want to do? We want to compute F, morally just F of 0 of A. So that's what the first step of the primitive recursion will do. And that will appear like this, where again, I've suppressed some case statements. F is 2, when we have some nested calls to F of depth 2, we have F of 1 of F of 0 of A, and it carries on like that. So there is no one infinite nesting path through this tree, but there are paths that do nesting to arbitrary depths. Yeah, so there's a slightly different character from the other one. Okay, and so I've done that just for the system T style recursor at ground type. For the higher type ones, similar form, just a little bit more eta expansion around.
I was just wondering, do you have to use bi-val?
You maybe don't really have to because this is going to start by evaluating. Maybe don't. Yeah, I'm not sure you really have to, but I make my intention clear that you want to start by evaluating n.
Is it supposed to say trim rack? The definition of trim rack?
Oh, sorry. That's a type. Yeah. Okay. Editing glitch. Prim rec. I changed from prim rec back to rec. That's supposed to be just rec. Typo. Thank you. Thanks for pointing that out. Okay. This is just meant to be a recursive definition of rec, which you can interpret using the Y combinator, or you could have this as a language primitive. Yeah.
So before you restricted if 0 so that its second and third arguments were naturals, but here I don't think they are naturals. For this ground type primitive recursor, they are. So if we're doing a rec n here, then all these sigmas will be n. So this A will be a natural. Oh, that's n. I see, but isn't.
Yeah, when you go to.
A is going to be n because it's going to match the first argument, and then F. Okay, now I understand. I missed that. That's very important. Okay.
Okay, that's fine. If you want the higher type ones, then you do have to. Well, yeah, there's a bit more complication, but it's not. It's fundamentally similar to this in terms of the shape of the tree. Okay, right. Okay, now if we think about ground type, just ground type again, there's an alternative way of doing primitive recursion, which is a kind of stricter way. So if you think about it, this primitive recursion I've got here is a kind of lazy character because it's possible for the function we get to be defined on n without being defined on n minus 1. Because it could be that the f we pass in here doesn't bother to look at its argument. So you could have rec a f5 being defined, then rec a f4 isn't defined. So there's an alternative, which is more the way Keeney set up primitive recursion, which is, we really do have to start at 0, 1, go through all of them, get all the results to get to a result for n. And that leads to a very different kind of tree. So again, we evaluate n first. If we get 0, we basically just return a. That's what this is doing. That's our base value. If we get 1, we look at what a is, and then and supposing the value of a is I, then we supply that value I to f of 0 to get our new value j, and that's what we return. If it's if n is 2, we do that twice. We evaluate a, then we evaluate f of 0 of what we've got, and then we evaluate f of 1 of what we've got, and so on. So there's no nesting here, it calls to f. It's just sequential calls one after the other. So these are these are different possibilities for ground type primitive recursion, and they have very different trees. Okay. How about iteration operators as opposed to recursion? So let's say think of iterators as in while loops as operations which might think of as having this type. This is a bit unofficial because I don't have some types in my language, but so we've got an operation. So think about sigma as the potential state that's being manipulated by a while loop. Okay, and then this function from sigma arrows sigma plus tau. That's what the body of the loop does. So it either it'll do something and then test whether we're in an exit case or not. If we're in an exit case, it will return an exit value of tau. If we're not, it will return the updated state, the new state type sigma, and then we get to go again. So given any starting state sigma, we can kind of go around this roundabout as many times as it takes until we exit at this tau exit point, or we might not exit at all. So this is just a sort of functional way of encapsulating what at least certain basic kinds of while loops do. Okay, so here's a version of this bulk standard iteration involving ground type data. So let's take both of these to be sigma and tau to be just n, and that's convenient because that means we can code this type n plus n as just n. We can do that within our existing type system, just using even and odd numbers for the two sides. So here again, here's a way of writing it. At each stage, we there's something missing. No, that's okay. Okay, we look at the. There's a very slight mismatch here, but it doesn't. We look at what we've got. We've said, is it on the left side or the right side? If it's on the right side, we return it. If it's on the left side, we extract what it is, and then we apply. There should be an application of f in it. I mean, right? I think yeah. I mean, case f of x here, don't I? Right. In case f of x is either we exit or we go again. Anyway, here's what that will be what the program looks like. Here's a procedure for it. So again, you see there's no nesting here. We're just sort of repeatedly applying f, and depending on what we've got, we may go again. So there could be an infinite path through here. So again, there is an infinite path through this tree, but it doesn't correspond to infinite recursion. It just corresponds to the infinite sequencing of these calls for f. So I hope that's sort of clear. You can do sort of higher order iterators where we think of the states that the while loops are manipulating as being of higher type. A bit more complex. I won't trouble you with the trees. But the idea there is that if f is the thing we're iterating, f is the operation we're repeating. In this case, if we exit after n iterations, then we get an n-fold nesting of calls to f. in the final state. And that doesn't happen here because we're at ground type. We evaluate the states at each stage as we go along. That's why I've called this a strict iteration. Okay, this is your bog standard iterator that lets you do, you can do it once you've got this in your language. You've got your Turing complete. You can compute minimization and sort of everyday iterative things. Okay, that's our tour of all these examples. Okay. And so what we want to do mathematically, I've told you what these NSPs are at each given type, but we want to make this into a model. We want to say what it means to apply an MSP of type sigma arrow tau to an NSP of type sigma. So we want to give a standalone definition of application that's independent of the definition of application in PCF. So I won't talk through this in detail, but what we do is we give ourselves a calculus of what we call meta terms, which is more generous than the calculus of terms, which is a place where we can do some computation, and within which the ordinary NSP terms appear as the normal forms. So you can see this grammar with capital letters looks very similar to the one for NSPs, but with some extra stuff. So we're allowed, procedures applied to other procedures. So this is a thing that's crying out for evaluation. We have a bunch of hopefully reasonable looking rules for doing head reduction. So we kind of, given a thing of this kind, we want to evaluate it to get an ordinary NSP. So we do head reductions as long as we can. If that gets us down to something of this shape, then we've got a bit of information. We've discovered a bit about our, so this case X is then a bit of real information about the tree that's the value of this. And then we just recursively go on and we evaluate these Q's and these E's. So as you can think of, as you evaluate this NSP meta term, an actual NSP proper will crystallize out from the top downwards as you go. So to evaluate the whole thing would take an infinite computation, but any finite portion of that crystallized tree will appear after a finite time. Very like what happens in ordinary Vernon trees, for those of you who know. Okay, so we can make this into a model. It's quite nice, it's well behaved, it supports compositional interpretation of our language, which agrees with the interpretation I gave earlier by just sort of head reductions, but it's this is given in an individualized compositional way. But now this is the punchline. This model is also very rich in interesting substructures. So there are submodels of this model. So for example, and we want substructures that are closed under application. Okay, so yeah, in fact we want a bit more than that. But so the very first example, if you just look at finite NSPs, finitely many nodes altogether, one can show it's not completely trivial, but they are closed under application. But that's not very useful because even the identity on N is an infinite tree, so we don't get structure there. But it's a good motivating example to think about. How about well-founded NSPs? So these are the ones where any path from the top down through the tree will eventually is a leaf. In fact, it's nice to also think about well-founded NSPs with no bottom.
But just to clarify, when you say finite NSPs, does that mean you can't have any case? Because cases are always
It basically okay. You could define finite NSPs to be, well, you can discount bottom nodes.
You're not allowed bottom, is that?
No, I could say the number of non-bottom, you could say an NSP is finite if the number of non-bottom nodes is finite.
So you can have an infinite number of bottoms from everything else.
Yeah, good, but yeah, I haven't quite, yeah. And anyway, there's a thing you can do there, but it's not really useful for our purpose because it doesn't give you a lambda algebra. But well-founded NSPs, they certainly do. And if you've got well-founded NSPs, I'm tempted to say that, that don't have any bottoms in them, they will actually correspond to total programs. And in particular, we'll see that everything you can write in with system T is going to denote a well-founded NSP. We'll come on to that. Now, some slightly more subtle things. There's a class of what I call left-bounded NSPs. So think about the nesting depth of applications. We saw examples where you had F nested. So if you've got a tree where there's some finite number D, that is a global bound for the entire tree on the nesting depth of applications. So we've got these applications appearing within trees, and we have applications within applications. But if they're never nested, if there are no nesting sort of to depth more than 14, say, then we have a left-bounded NSP. The reason for the name is that when we're following paths through the trees, I'm thinking, and if we're sitting on a case node like this, I'm thinking of the branch that descends into the X queue here, or into one of these queues, as a left branch, and one that descends into one of these E's as a right branch. So these have quite fundamentally different characters, these left and right branches, because left branches have to do with nesting, right branches just have to do with sort of sequentially doing things in order. So left-bounded just means that there are no paths. There's a bound on the number of left branches within any path in the tree. These are a nice substructure. They're a lambda algebra. And then we have left well-founded NSPs. These are ones where there is no infinite path that contains infinitely many of these applications. So they can be unboundedly, you can have unboundedly deep nesting, but no actual infinite nesting. Now, you ought to be wondering by this stage, how do these relate to, how does this classification relate to all the examples we've seen so far? So,
sorry, John, before you leave that, I don't have a good intuition about left and right. Is left versus right something we determine at runtime, or is it determined just from the structure of the tree itself?
It's just determined from the structure of the tree. So if we have case xq of I ei, these q's,
Yeah.
we think of these q's as left subterms and these e's as right subterms.
Yeah.
That's all. So we take a left turn when we descend from this node into
I'm
one.
sorry, but I don't understand what you mean by descend into.
So,
the node of the absolute syntax tree of case is the legs going left into the XQs, the legs going right into the EIs.
So think about one of these NSPs as a tree, and we're interested in whether it has infinite paths from the root going downwards.
Oh, I see. So you're saying that the left bounded means the Q's are all finite, but the EIs might be infinite.
Yeah. You can have a path with infinitely many right turns to an EI, but there'll be a bound on the number of, there's a bound on the nesting depth. So that will mean from a certain point.
I see. And then left well founded is there might be an infinite number of them, but they never end in bottom.
They never go on for they never go on forever. The paths never continue forever. So, for instance, if you think about the Y Combinator, it had this infinite chain of nested applications of F. That would be an example of a non-left well-founded tree.
I see. Okay, thanks. Sorry that I was dense there, but I was really lost. So I'm glad you took the time to explain.
Okay, so let's just try and very quickly. Right, so we can see that these various beasts we've introduced. So this is the good old Venn diagram. We've got well-founded trees, we've got left-bounded ones. They have quite a substantial intersection, and then left well-founded embraces both of those. But every region of this Venn diagram is populated, in fact, by one or other of the things I've mentioned. So from this, we can see straight away that, for example, so because the Y Combinator its tree isn't left well-founded, we can see straight away that it's not going to be lambda definable from any of this stuff that is. So if we had a programming language whose primitives were any or all of this stuff within the left well-founded world, this NSP for a Y combinator would remain out of reach for it. So we can see some expressivity distinctions. But that's not what we're most interested in. Who cares if a certain NSP is definable? But these NSPs have what it takes that you can prove stronger things about them. So with a bit more work, you can prove that not only is Y sigma not a left well-founded tree, but no NSP that's extension equivalent to Y sigma. So there's no NSP that will give the same observable behavior as Y sigma could possibly ever be left well-founded. That's a thing you can do by sort of combinatorics and case analysis on the trees themselves. And then that tells you that up to observational equivalence, we can't define this Y sigma from all this stuff that lives within left well-founded.
What's the BR thing at the top right?
BR is bar recursion, which yeah, so hoping I can say a bit about. I'm sorry once again. Okay, this is really the punchline. I've got to the punchline, and so likewise, what I've said about Y sigma applies here. So we can see that rec sigma can't be defined from these left-bounded primitives, and there are quite a lot of there are other results like that you can obtain. So this is the punchline. There's one more official slide. There's a bit on bar recursion, and then there's some extra slides on game semantics. Stop there for now.
One quick question.
That's a nice punchline, John.
Thank you.
Did I miss it? Did you explain what the superscript str means?
Oh, that's strict. So I mentioned that there was you can make a distinction between sort of the primitive recursor, the way you naturally get it from the rewrite rules, and a strict version, which is the one that
By value.
yeah, strict in the sense of by value. So at ground type, we can make strict versus non-strict distinctions.
Raj?
The system T then correspond to all the left well-founded.
System T, everything system T denotable lives within the well-founded world.
Exactly.
Not exactly. Guess what? They are well-founded trees whose ordinal height is at most epsilon 0. They're not even all of those trees, but you get a decent fragment of the well-founded world from system T, but
not all of it.
not all. It's well-foundedness is a logical complexity terms of pi11 condition, so there's no hope of having something that's going to catch all of them.
Thank you.
Last question from Jesse before we go on.
So can you define strict recursion? Wait, so you said you can't define recand from the left-bounded stuff. Are there other inexplicability results that you mentioned yet about the strict level?
Expressivity results about this one.
Yeah, inexpressive.
There's a few more. So the other place I've gone is, supposing we decide, well, you know, rec n and rec n strict, they only differ on sort of partial arguments. You know, there's a sort of so supposing we decide we didn't care about the behavior of our programs on partial arguments. We're only interested in the behavior on total arguments. So you know, we're being more generous in what we regard as equivalence. So you know, then we could say these agree, but even if we're so it's a theory. So one of our theorems is that even if we're only interested in total arguments, you still can't simulate the next recursor, the type 1 primitive recursor within the left-bounded world. So this rec n isn't computable with rec strict n and even plus ground type iteration. So yeah, I mean, you sort of get get into fiddly reasoning on trees, but the point is the trees have that information there that let you do this kind of reasoning. They give you something to get your hands on in a way that, like Scott domain, Scott domain perhaps.
Yes, that's fair. Question. Could you show a slide?
This one.
Yeah.
This is my favourite slide, really. Yeah.
It's lovely. Someone was asking about, I can't remember who it was. Jesse asking about whether, this is system T basically with the primitive recursion or subset system T. I thought we could define iteration from recursion.
You can define iteration
but-
from so this rec is prim rec. These recs are prim recs.
So that iter we're seeing, the strict iter we're seeing in the left bounded thing there. What do you mean by inference? I guess it depends what you mean by.
This is unbounded. This is like
It's wild.
this is like while for ground. It's like or minimization or something like that.
Right, we can't define that from rec at ground type or.
No, because this
primitive.
rec is a total. This rec is prim rec. So this is a total rec.
So if we had primitive iteration, we could define that from primitive recursion.
In general, iteration is definable from a version of iteration is definable from a version of recursion at that level.
Right.
But not so once you've got this recursion up here, you can define everything. You can define once you've got all these recursors, you can define all these iterators.
Right, my point is you could define a more primitive form of iteration inside system T.
Within system T, you can only do bounded. It's like for loops. It's like for
Exactly.
loops. Yeah.
Yeah.
So yeah, think of it. This is the world of for loops, if you like. So it's not at all. It's not surprising at all that this lives outside that world. It's perhaps less trivial that this rec lives outside this world. Well, it is. It is less. It is less trivial.
No, I think that's where
Yeah.
I'm getting confused.
Yeah, but you get a feel of these different flavors of how much nesting you're allowed and the difference in character between these trees. For me at least, this is illuminating. You get to see these distinctions.
So, like in the grammar of NSP, let's say remove the bottom. I mean, let's say so in the grammar of the NSP,
Yeah.
let's say remove the bottom from that. What am I left with then?
Remove the
Bottom.
Remove the bottom. Oh, okay. Yes. If you remove the bottom from that, you get a structure that's not closed under application because you have two NSPs without bottom. If I apply one to another, it could generate that. You could have two NSPs with no bottom in them, but they will generate an infinite computation on the infinite interaction between them. So there are three ways a computation can give a bottom. You can have a bottom in M or a bottom in N, or no bottom anywhere in sight, but there's an infinite interaction. So you don't get a useful substructure by looking at the NSPs that happen not to have bottom, unless they're well founded. If they're well founded, then the interaction will always terminate.
So follow up on your answer to that question. That kind of infinite computation that you're talking about, wouldn't that, I mean, I was thinking until you gave the answer that would be, a tree that is very nested in the way, but you're saying it's not even that, you can't write it at all, like even with infinite nesting. I don't know if the question makes any sense.
Not quite. You don't have to have infinite nesting to get infinite computation. You can have just an infinite sequence of right, so from your point of view, right branches. Yeah.
But what do you need as to be able to write bottom for infinite when you can have infinite computations that do not include bottom?
Yes.
But NSPs are normal forms, right? So if if it continues to compute forever, you will not find a normal form.
Yeah, you won't find. Yeah. So I think it connects with Sam's questions. The bottom is a slightly writing the symbol bottom is potentially slightly misleading because you wouldn't compute the presence of the bottom. You would just fail to compute.
So why do you need it in the grammar? Which is what you're asking.
This is a model. You need it for a model. even though we can't actually compute it. Because there are programs that don't terminate, so you get some way of talking about those.
Yeah. I mean, you could set these things up as trees given by partial functions from node addresses to node labels, and then a bottom would just correspond to the undefinedness of the label at a certain node. But it's more readable to do it.
I don't think I understand this.
Yeah, but Sam, you're saying that's this forever, everything is bottom, you just, we didn't hold that right, so we use forever, why do you need bottoms and just get in?
Yeah, that's my question.
So it only computes forever, but there's no external, but it's just an internal dialogue between the two participants. It's nothing, you have something of type sigma arrow n, and you apply to something of type sigma. You're hoping to get just a number out of it. If you don't get a number, you don't see anything else.
Doesn't this have something to do with the definition of head normal form, which means that when you have a recursive head normal form, maybe the term becomes arbitrarily large, and the computation of the deep head normal forms never terminates, but at each level, you always have a term starting with a variable and applying
that can happen, but that's different from, I think, what we're talking about just now is even the attempt to compute, a single node in the tree can give an infinite computation that just fails to terminate.
So we know that the distinct NSPs are not necessarily semantically different. But can you prune them somehow to get semantically different representations? So you said that I can have two trees representing the same program, but they're different because of unreachable branches. Prune the unreachable branches.
No, we'll come on to that next time. We'll talk about different kinds of observational equivalence. What happens if you add a bit of state in, and which would let you.
Yes, yeah,
But I will say that. If you want to take I'll just flash up some of my game semantics slides. So, this model is actually isomorphic to a certain game model. In both cases, if you take the extensional quotient, you get something that's fully abstract. But we really don't have a handle on this extensional equivalence stretch. This is Ralph Loder's result. So even in the finite tree case, this is undecidable. So X is arguably not.
The superscript 0, I've missed that.
Oh right, the 0 that definitely is closed. Yeah, that closed NSP. You can have
Closed.
NSPs can have free variables in general.
Right, without free.
This just means no free, but every variable is bound by a lambda somewhere further up in the tree.
So maybe this might be what Donna was saying, but I just wanted to clarify. So you said in the beginning that this PCF is kind of in the middle.
NSPs are
NSPs are a middle step towards the denotation semantics. How do you do the second? How do you get to the denotation?
How do you do
from?
Yeah, you can give it. You can directly give both of those semantics. So, I mean, NSPs, because they're infinite things, you have to give the semantics of those as a kind of limit. You can give the semantics of any finite finite approximation to an NSP,
and then you
just in a normal sort of way, and then you take the limit of the, the Scott world has limits in. That's what its main purpose in life is. So, you can directly define both those semantics and prove that they compose to give the classical thing. I should say as well, of course, there are other models than the Scott model for stable domains, other things, sequential algorithms. Something that I might touch on next time is that actually any reasonable interpretation of PCF in any model at all, where reasonable means something technical, will factor through NSPs. Yeah, we'll come to that. A model would have to be very weird for its or very, very intense. We'll say a bit more about that next time. But there's something canonical about that.
So how do, like, continuing on that topic, how do the clean computability fit into the NSPs?
Yeah, so it's like, just as I showed you from a PCF term, you can grow
Yeah.
an MSP, but from a Cleany index, and in Cleany setting, programs are just numbered, everything's coded up as numbers. But there's a number that codes up a certain algorithm, and from you can just unpack that algorithm. You can just grow an MSP
Right.
From it.
And I assume there's some similar sort of relationships to your, to the Venn diagram.
Right.
Thing.
Yes. There will be some analogous results in the Cleany side. You can read off from the same.
Right.
What the theorems prove actually tells you something on both sides.
Yeah.
There are some things I know about on the PCF side that I've not.
I mean, obviously, just through the coding will.
Yeah. So, for example, the Cleany version of. If we look at. Sorry. Not this one. Nothing agreeing with total arguments on rec on. That means something on the Cleany side, which was actually which actually answers a problem that was open for quite a long time in the 70s and had been solved by very, roundabout indirect methods. But well, actually, the question was: is there a function? Is there a total function of a certain type that can't be computed in with this? Yeah. Sorry.
Phil?
So thanks again for that, John. So near the beginning, you said, oh, bival makes for very natural correspondences here. Yes, there is something that's existentially equivalent to bival, but bival is very important. But I never understood why. So can you go back and...
Let me go, again, this will perhaps come into more focus next time, but going back to, all the way back to here. Yeah. So I showed you what the tree for bival looks like for the strict application. Okay. So that particular tree is an example of a tree that's not denotable by a pure PCF term.
Oh, okay. So can you go back to the previous page that has that?
The page that has the tree for bival.
Yeah.
Oh, that's the latest. That's
Yeah.
Okay. That's this second one. This second one here.
Right. So if I define something that just right, it's basically the identity function on natural numbers using fixed point, that would force my argument. Right. I couldn't use it until I.
Yes, you can make it strict, but then you will if I understand what you're saying, you'll keep reevaluating that argument lots of times if you do it that way. So you'll be strict.
So maybe I should ask for this offline, but maybe it'd be nice if you could write out the equivalent bival that can be written in PCF, and then show how those have two different trees. So that'd be very useful for me.
Is that what I've done here? So here's I see the thing that you're proposing. If you so here's would you like to email me a PCF term for a version of bival, and I'll see if I endeavour to work out the tree for it. Would that?
Okay, that's fair enough. Thanks.
To make sure I'm answering what.
But it basically ends up branching to the left, right? Not like here to the right. If I'm following.
Well, it's sort of anything with recursive calls. Yeah, you'll get. It sounds like you'll get some left.
So the interpretation from PCF to this NSP is very classical. You need a lot of pyramid.
You need
a lot of experiment. From the interpretation.
If you want to write these bottoms, then Yes, it's classical.
Presentation of your PCF terms to its NSPs, you need to say whether if the term terminates or not.
Yes, but if you did it in a more constructive way where you didn't actually insist, well, you just said an NSP is actually a partial function from you can.
Oh, so there is.
You can do it more constructive. You can do it more constructively. More computed.
You still need bottoms.
Well, you need the possibility of non-termination, but you don't need to know whether you've terminated or not.
So I was just realizing from that bottom discussion, is it the case that given any NSP with bottoms in it, one could express it with no bottoms? An equivalent one without bottoms?
By just repeat just time-wasting evaluations of, as long as you've got at least one argument around, I guess. Yeah, you can just get a case X of
But the
that
bottoms
case
are really
X.
useful in practice if you want to try and write down a tree.
And also they would be different. I mean, they would be a different, you know, it wouldn't be correct to say this expanded tree was the D. Yeah, you would see the difference when you try to add more features to the language. So
might it actually be contextually not contextually equivalent?
I mean, within PCF itself, you couldn't distinguish bottom from this infinite time wasting evaluation, but
With sufficient effects, possibly.
there's more on this next time.
Can I? Right, thanks. So correct me if I'm wrong, but from the back of my memory, when we have in the on-type lambda calculus different term trees, there is a separation result that says that there exists a list of arguments that when applied to both original terms,
if there's a difference here, you can distinguish.
It ends up in 0 and 1 in the two different original terms, right? So you can apply the same sequence of arguments
Yes.
to the two different trees and get the results that can be discriminated.
Yes.
Does the same hold here?
We don't get that here. We don't. Yeah, there are a lot of.
So that was that thing that was mentioned, right? That we have multiple different trees that denote the same.
Yeah,
function,
you can't
right?
distinguish
Because of unreadable
within
aspects, yeah.
So I can go.
This isn't a super well formed question, but going back to the Venn diagram, you have some very nice categories there. Well founded, left well founded. So I noticed they all potentially talk about the lengths of the branches, or potential lengths of branches. Are there any other? I take it this isn't. There's a more fine-grained picture here, and there are other kinds of categories, things, classification.
I believe that there are lots more substructures. I believe it's a rich world, and there's more waiting to be explored.
The kinds of sets you would describe, like, or the other kinds of sets of NSPs, which.
What some other ones?
Yeah.
Some other ones. Ones that are useful, easy. There's sort of.
I have a question about that.
Yeah, I don't have an easy. I believe such things exist. I'm sorry, I don't have an easy example to give for that. But, yeah, sorry. So, but anyway,
Does anything interesting happen if you change from natural numbers to a finite set?
cut down to a finite set. Yeah, that's sensible to do. I mean, you still get this undecidability of observational equivalence. But you have, okay, finite set, you could still have non-computable trees because they could still be infinitely deep. So, yeah, it doesn't, sensible thing to do. I can't think of anything to say about it.
Could you interpret PCF?
Yeah, the finite tree, that's what finite tree PCF, there's a sensible, thing to say about that is you don't need the Y combinators. Everything you might want to take a fixed point of will find its fixed point after some finite number. Oh, no, there is something to say here. If you take a finite tree PCF, in the Scott domain as well, it means all your types are finite. Okay, because they're just functions from finite sets. Right? In the NSP world, the interpretations of some of these types are still infinite. So there are, well, like we have this thing of, how many times do you want to evaluate X? You can evaluate X as many times as you like. So it's a bit.
But if you don't have the Y combination, that means you're terminated.
You don't have the Y combination, you'll stabilize, but you can still write down.
Without the Y combinator, I can't write a non-terminating programming in a simply typologic calculus.
No, unless you have, the only way to non-terminate would be to reach a bottom. You can't have any, you can't.
You can't. Right. You can't express anything that's equivalent to bottom if everything is.
I'll do. So start from PCF, chop out over a finite place type. People who do finite for PCF, they normally say, well, if we're getting rid of the Y combinator, we better add in bottom as a.
But that's the only thing you can observe is divergence, right?
Oh, so you can only, but then you know where bottom is because you've written it explicitly. You can't have unknown bottoms.
Yeah, well, you can move around, right? Because we have functions. Really selfish. So looking at this picture, so I guess I'm not an expert. Rational fixed points, right, would be a very more intentional model that doesn't factor through NSPs. But you can look at the NSPs that come from rational fixed points. And that would be a submodel or
what is a rational fixed
so it's like you expand a finite kind of a function up to like yes, trivial. You know this class?
I'm not very.
Okay, we can talk about it.
Yeah, that sounds interesting.
Okay.
But, okay, so you're saying there are some interesting models that wouldn't.
Yeah, maybe it's a submodel. Maybe it's like if you look at the NSPs that are rational fixed points. Okay, thanks. Sorry, that was me being selfish.
Okay.
Any more questions? Do you have something you want to say before we go?
I think I'm okay. Sorry again. There's still a lot I haven't touched. I will put up my bar recursion slides just for just if anyone wants to quickly look through that and wants